So hello everyone, my name is Jan. I will talk here about performance, which is a thing that was bothering me for a long time. I really love Python for its simplicity and elegance, but whatever I do, I find it to be too slow for me. So I was thinking about how to improve this performance, and today I would like to share my experience with a tool called Cython that can be used for optimizing your Python code to run as fast as C code. So in this talk, we will first take a look at how fast, or more specifically slow, is Python, and then I will introduce Cython, show some example usages, show some comparisons with native Python code, and in the end, I will share some general optimization tips that you might find useful when you decide to actually optimize your code. So the motivation for this, some people say that nowadays hardware is really cheap, so you don't have to bother like writing fast apps. You can just throw more metal on it and it will work fast. But in some cases, this doesn't help at all. For example, if you want to achieve low latency, you cannot just use more computers because the frequency of our CPUs is bound by some physical laws and it cannot grow. And parallelization doesn't always help. And if it does, it's really complex. It can be very hard to synchronize data and lock all the shared parts of your data, and it can be very hard to debug the issues that you will get with your parallel code. So the first obvious thing to do when your application is slow is to improve the efficiency of your algorithms. Write something smarter, faster, more efficient, but this has some limits, and even if you do it, it gets your code more complicated, harder to understand and maintain. I was taught to use, like if I want to implement priority queue, I should use some really complicated Fibonacci heap sets of trees and then prove mathematically that it's faster and it works. But when another computer programmer comes after me and reads my code, without knowledge of computer science, he will have absolutely no idea how the data structure works. So it's a good idea to optimize the runtime of the Python interpreter in such cases. We will take a look at this simple benchmark of recursive implementation of the well-known factorial function. It's really simple. It could be improved by using loop instead of recursion, but leave it like this. This is really slow, even for slow inputs such as 20. This takes 2 microseconds, which is 2 millionths of a second. And we will show later in this talk how to improve this. So in Python, even a simple function call is quite slow. It takes 60 nanoseconds on my computer. And function call is basically everywhere in your code, right? Like good-looking code should have really small functions, like code separated by some logical levels of abstraction. So you should use functions a little, but even the functions call are slow. In C, function call is 20 times faster. It takes 3 nanoseconds on my computer. Addition and arithmetic operations is slower in Python. This factorial function is 30 times faster in C, and some string algorithm example that I will show later is like 120 times faster in C or Cython compared to Python. So I have mentioned Cython a lot of times, but what it really is, Cython is a compiler for Python language, or some superset of Python language with some added syntactic features that is able to compile from Python code to C, and that obviously runs much faster. So beyond just speed, Cython is useful for several other things. You can wrap C libraries with Cython and then like convert the C data types such as vectors into Python lists, for example, because Cython understands both the C world and the Python world. Using Cython is really easy because you are just writing Python that gets compiled into C, so you don't have to learn a lot of new stuff. You don't have to switch languages. You don't have to hire programmers that know like some faster programming language for some parts of your code. And then Cython also gives you some tools how to compile your code and distribute it. So distutils and setup.py has support for compiling Cython. So it's just adding one line into your setup.py. I will show this later as well. So if we take a look at the factorial function and try to improve it, I can, in my Jupyter notebook, I can just use this Cython keyword, and this cell will run in Cython. If you were using it just in some file, you would just rename pi into pix and add the compilation instruction into setup.py. And then I can just copy-paste the code here and compile it into C. I can see in this output what exact C code was generated by that line. So for example here, we can see that this is an integer and something comparison. We don't know what n is. It could be integer, it could be complex number or something. So we have to call some generic comparator that is obviously slow in Python. And then we have to evaluate if that was true and then execute some if condition based on that. But even though this is slow, it's still faster than the original Python version, and it's twice faster without us even doing anything with the function. I just copy-pasted the code and it's twice as fast. So that's quite cheap win. We can go further and supply some additional information to the Cython compilator. We can say that we want this function to be compiled into C with Python wrapper around. We can say that the parameter is a long type. The function returns long as well. And the rest is the same. I don't have any local variables to declare here. And this is actually like 30 times faster. It's just 60 nanoseconds on my computer. And we can see that this was completely compiled into C. There is no yellow color in this listing. Yellow means Python call. So your goal when optimizing is basically get rid of the yellow color, right? No yellow color means fast code. So let's get to a more complicated example. I found like one of the slower string functions on Wikipedia, some really slow example function that finds longest common substring that is contained in two strings S1 and S2. And I started optimizing this function. So here, for example, I say that Cython shouldn't check the bounds of array access. If you access some list on like negative index or non-existing index in Python, it will throw up an exception, right? If you do this in C, it will blow up your program. It will just crash violently without you knowing anything about what problem caused it. So if you want your program to be fast, you can disable the checks and hope it works. Yeah. So I had to modify the body of this function, declare all the variables here. For example, I define the type of len1 variable to be integer. Here I use a shorthand for declaring more variables at the same time. I even have to declare the for loop indices here. I replaced list m with NumPy array because it's faster and it can be accessed directly from C. So this is uninitialized. This contains some random numbers at the beginning. So I had to initialize the important parts as well. And then I could just leave the rest of the method the same. There are some two-nested for loops, which are the cause why this function is so slow. And if we take a look at the result, you don't have to read the letters. It's not important. The important thing is that it's not yellow a lot in the for loop. You see, just one line with some Python call. It's because of Unicode, because C doesn't support Unicode, so we have the Unicode strings here, and we have to get the one character from them, and we need Python to do that for us. So the result of this implementation is that this function is actually 120 times faster than the original function on some long string generated from lorem ipsum generator. Yeah. Even the common substring is quite long. I was surprised by that. It's just a random paragraph. So Cython can also support C++, even with its containers. So here you have this line that enables C++ language, and then you can just import C++ vectors or strings or anything really. And what's even more interesting, Cython can convert this automatically. So for example, here you have conversion from iterator into C++ vector. Then you can release GIL. That's really practical when you want this to run in parallel or in multiple threads. You can work with the C++ data type, and then you can convert it into list and print it with Python print. So it's pretty convenient. You can also use strings and convert between strings and bytes objects in Python without having to do anything again, as in this example. You cannot convert between C++ string and Unicode, obviously, because that's two different things. What's interesting about Cython is that it also supports parallelism really easily using OpenMP library. You can be familiar with it if you code in C++. It's open multiprocessing library, and it supports constructs like this. This is a for loop that executes this inner part in parallel in multiple threads that are automatically generated. So here I have some vector, and I want to assign to it like parallelly several threads at the same time. So here I assign the thread number, the thread identifier of several threads, and here I say that this should be run in parallel and with GIL released. So I cannot use any Python functions, any lists or something like that here, but the C++ vector is fine. And we can see that this function spawned like 4 threads, and each of the threads executed 2 iterations of this loop and saved those thread numbers into the vector. So how to create or how to convert your Python model into Cython if you want to optimize it? You can just rename it into PyX and then add this line X models into your setup Py that will compile it each time you want to update the model. So the downside of this is that you have to execute this command every time you change the code to update the library. It will process your Cython model into C and then into some shared library, which you can import as usually into Python interpreter. The downside is that you have to supply some dependencies to each of the computers you want your code to be run on. So the computers have to have the compiler and optionally Cython. It can be tricky on Windows to get GCC working, but you can use Anaconda Python distribution to get the compiler really easily. And if you want to distribute pre-built packages, you can use pipwheel to do that. You just have to build a version for Windows, Linux, 32 bits, 64 bits, and so on. You can even mix Python and Cython in one file. You can just save it into the original file name .py file and decorate the functions that you want to have optimized. And if the running machine has Cython installed, it will compile it. If it doesn't have Cython, it will just use the slow Python version. Okay. So this was quite ugly with those decorators. You can also use the Python 3 annotations, but this is still in development in the Cython project. So I don't recommend using it yet, but it's a really promising and nice feature. You just enable it like this, and then you can use Python 3 type annotations to supply your variables. And it's really clean and fast. There is one alternative to Cython. You may know JIT compilers from Java or C#. It's an elegant way to make your code faster because JIT compiler observes the execution of your program. And if there is some slow function that gets called repeatedly, the JIT compiler compiles it at runtime and then executes the native code. And it's much faster, and the programmer doesn't have to do anything, so it's practical. But it's hard to implement, so CPython doesn't have support for this. There is an alternative interpreter called PyPy that supports this, but it's not 100% compatible, and its development lags behind CPython. So they have just 3.5 in beta state. They have some GIL-less branch that looks very promising, but it's still in development. And PyPy doesn't support some C extensions like pandas that were mentioned yesterday. So if you don't need any unsupported features by PyPy, you can give it a try. Your code might be several times faster without any effort needed, so it might be easy win. Yeah, this factorial benchmark was 3 times faster than in standard Python. That's still slower than Cython, but it's good. So to the optimization tips, they should be pretty obvious if you did some optimization before. The first one is that you should always profile before optimization, because if you have more complicated code, you cannot be sure what's slow in there, and you could optimize something that is actually not the bottleneck of your application. You can use the cprofile tool. It's the best you can get, I guess. You can also automate your benchmarks and profiling and use the same code as for your tests, which is really practical. I can recommend that as well. And you can visualize the benchmarks using SnakeWiz. So for example, you can see how or where your function spends execution time. So for example, this function stays a lot of time in this another function. And it's much easier to comprehend for human being than some text statistics that you can get from cprofile. So second tip is that some methods might not be worth optimizing because optimization makes your code complicated and it's harder to read and maintain. And if the function takes just like 5% of runtime, then even if you speed it up 5 times, it's just 4% speed up overall. So it might not be worth it. 4% is not even noticeable by person using your program. And the last tip is always test before optimizing, because if you don't, you can change the behavior of your functions, and then you end up with code that works and crashes really fast. So that's all. Thanks for listening. If you want to chat about performance or about what we do at QuantLane, you can find us here or at the party tonight. We are very friendly, even more after some beers. So come to chat with us. Thank you.
Thank you, Honza. We do have some questions. I think you answered the first one. Have you considered PyPy and why did Cython win? Do you want to add anything?
Yeah, Cython is just faster, much faster than PyPy.
Right. Any advice on how to decide between Cython, NumPy, C extensions, PyPy, Numba, and whatever else?
So I like Cython, obviously. Cython can be combined with NumPy. I recommend NumPy. Actually, I didn't mention it, but Python lists are really slow. Like, if you can use anything else for primitive types such as integers, just do it. So NumPy is good for performance. C extensions, I don't recommend it because you have to write in C, and Python is just better. And PyPy, if it works for you, then it's easy way to get some performance boost. And Numba, I tried it and it doesn't work most of the time. So next question.
Okay, thank you. How do you debug Cython? Through GDB or something?
Yes, I use GDB most of the time. I was a C++ programmer before, so it's not a problem for me. GDB is good.
Would you mix interpreters? For example, write most of the code in CPython and only parts of it in PyPy?
It depends on how separated this is. If it communicates over network, yes, it's a good idea to do it.
Okay. And maybe off topic, is there a good snakeviz for memory usage?
I'm not sure. I don't know about any.
Okay, thanks. Any more questions from the audience? No more questions. Oh, here's one. Thank you.
You talked about C extensions that you shouldn't do because you will have to code in C. But what if you already have a C library that already does that job faster? How is the best glue code you would recommend to link Python software to C software?
Oh, Cython, of course. Yeah, you can use Cython for translating the data types, for connecting the calls. So, yeah. I also tried PyBind 11, but I had some troubles with its bugs. So, Cython is just better. Use Cython. It's good.
Any more questions? If not, then thank you, Honza.